Hi everyone, today we will be presenting our paper on TransforLearn, interactive visual tutorial for the transformer model. Here's a brief overview of what we will cover today. As the evolutionary tree shows, transformer has become the primitive structure of the now popular large language models. And more people are curious about principles of transformer. To clarify the research status, we invited domain experts and relevant students to conduct the preliminary study. Students felt confused mainly in complex structure, data transformation, and abstract downstream tasks of transformer. The chart below shows the specific problem encountered by the students. It is worth mentioning that many students find it difficult to understand the QKV matrices and the operation between them in attention. For lecturers, they express the need for the improvement of teaching methods, especially they want students to have hands-on experience with interactive tools to increase students' participation in classroom. Meanwhile, we summarize related work from the following three aspects. As we know, most visualization systems are expert-oriented and focus on semantic understanding, so we think these are not suitable as tutorial tools. Additionally, there exists no visual tutorial specifically explaining underlying principles of transformer. Blogs and videos for tutorials rely on graphics and text, and the existing visual tutorials for transformer are text-based, and there is no interactive visual tutorial designed for transformer. Consequently, there is a pressing need for comprehensive, interactive, and visually engaging tutorial tools tailored for transformer to bridge this educational gap. We present the following design objectives for TransforLearn corresponding to the four tasks. TransforLearn should demonstrate implementation and module interactions in a visual and interactive way. We also hope that TransforLearn can align the abstract model with specific tasks so as to help users to reap self-directed and immersive learning experiences rather than the reluctance of boring concepts. We designed the visual interface for the classic transformer framework with different parts corresponding to different modules. We follow the structural characteristics of the model, visualizing the various parts from the overview to the model details. The main visual metaphor used in our work is to map the matrix to corresponding color scheme to form the heat map matrix. Corresponding text descriptions and interactive guidance are also inevitable. For complex modules such as encoder or decoder blocks, we provide flowcharts of abstract concepts, which also serve as an interface for the user to interactively explore the data flow and the implementation process of each module. At the same time, we propose two exploration modes to provide beginners with a pathway from abstract understanding to practical implementation. The overview of model structure and the hierarchical relationship between models became clear with architecture-driven exploration, and users can continually explore the inner layers and study the formula parameters through certain interactions. For example, clicking on the interactive interface in the embedding module can explore specific implementation of word segmentation and positional encoding. Similarly, the flowchart in encoder or decoder block supports further exploration of attention mechanism, layer normalization, and feed-forward networks. Clicking on attention mechanism will also show the second-level detailed operations. Based on task-driven exploration, changing decoding time step in real time helps users derive further insights, such as data flow changes and structure features. The interactive of these two explorations and the practical task solving of TransforLearn will be specifically demonstrated in the usage scenario. Our target users are beginners with a foundational understanding of deep learning who are eager to gain a comprehensive understanding of transformers. Additionally, we envision TransforLearn serving as a valuable teaching aid during lectures. The self-study scenario video will be played here to show TransforLearn's interface, interactions, and exploration modes. The user in the scenario used TransforLearn to explore the generation of Q, K, and V matrices and embedding numerical features. Next, we will show the usage scenario of the self-study. The student entered the sentence, "I have an idea," and explored the system by architecture-driven exploration mode. By observing the sequence vector and the textual descriptions, the beginner finds the encoder's embedding part provides an intuitive understanding that the participle is transformed into long sequence data as model input. This insight inspired him to find a suitable method for handling high-dimensional time series data to match the model input. Continuing the research, he explored the extraction of data features by using the attention mechanism. By clicking on the head button, along with the aid of color mapping and textual explanations, he discovered that the weights and biases used in the QKV generation are learned through training. Switching to the task-driven exploration mode, he discovered that the attention score matrix of the last block exhibited obvious color coding for the phrase "have an idea." This led him to consider the varying importance of each head in extracting different features. Finally, by understanding the lower triangular matrix in the mask operation, he gained clarity regarding the confusion that post-order information might interfere the prediction process. Evaluation consists of the following three parts. Before the user study, we compared the performances of existing tutorials and TransforLearn and found that TransforLearn can more or less complement these methods. We invited 18 volunteers to participate in controlled experiments and divided the control groups according to their individual user portraits. We also collect feedback from users about how they feel with TransforLearn. The user-controlled experiment consists of 5 steps. Especially in observable study, participants were asked to complete several tasks to assess learning efficiency. The experimental results show that TransforLearn not only improves learning efficiency but also brings students learning initiative and divergent thinking. In the communication and interviews with users, apart from positive reviews, we also received some suggestions, which leads to our discussion and outlook on this work. The first problem is visual distractions caused by the large amount of data. We use sensible color mapping and convenient interactions to help minimize the interference. To help non-experts comprehend transformers, we inevitably sacrifice some ability of semantic understanding. We plan to explore richer visualization forms to address this issue. Meanwhile, we hope to further generalize TransforLearn to different model variants, tasks, or modalities to bring more experience to beginners. We also need to make the assessment of our work more complete and in-depth. Thanks for your listening. Happy to answer questions about our work, and welcome to visit our homepage.